Hello my dear students, how are you doing? So today we'll be ending the module of vector calculus with the last topic, that is the Stokes Theorem, and after that we'll be starting afresh with another topic in engineering mathematics. So let us watch the video. So hello guys, we are going to talk about vector calculus Stokes Theorem part 9 today, and with this we'll be wrapping up vector calculus. So to start with, we'll be going with the concept of vector calculus. So let us first of all understand what is the concept of vector calculus. So if S is an open surface bounded by a closed curve C and F is a continuous and differentiable vector function, then this is the formula for vector calculus. Now, one thing I will tell you, in the case of Gauss divergence theorem, we have already come across the fact that this is basically a transition from the double integral to triple integral and vice versa. Here is a little difference. Here is also there's another transition, but this time it is from a single integral, that is one integration, to two integration and vice versa. So this is basically the concept of Stokes theorem. And as you can see here, there is n cap. N cap is nothing but the outward normal at any point of the surface. If you are considering a surface, if you want to make it 3D, so there will be two normals, one going upward, one going inward. So we are considering the upward or the outward normal of any point on the surface S. Okay, now let us go to the next part. Now comes a question. So as you can see here, we have to evaluate closed integral C, which is given as sine z dx minus cos x dy plus sine y dz, by using the Stokes theorem, where C is the boundary of the rectangle defined by the limits 0 to pi for x, 0 to 1 for y, and z equals 3. So this is basically the question where we are given the limits in front of us. We just need to apply the theorem of the Stokes theorem and we are going to find the answer. So the question is not a difficult question because we have already been given the limits. We don't need any kind of hard work in order to find out the limits and all. Only one thing we have to consider: which limit should be considered for whom and how we are going to categorize the limit. That is the only thing that we'll be considering here. Otherwise, everything else is given in the question. Now let us move forward to the next one. So first thing that we have to do is, as you have seen in the formula, the first thing that we are doing is, see here, if we are converting the singular integral, the closed integral, into the double integration, so we have to do the nabla across f, that means the curl of the vector f. So as you can see, the question has been given in the singular integral, so that should be f dot dr, that has been given to us, and we have to convert it into the double integral, that is nabla across f. We have to do first. So the first step is to find out the curl of vector f, which is very easy. So we have to just put the values. We know the nabla stands for I cap del del x plus j cap del del y plus k cap del del z. So the first two rows are meant for that. The first row is meant for the position vectors I, j and k, and the second row is meant for the differential operators for x, y and z. The third row is meant for the vector f, which has been given in the question here. It is sine z dx minus cos x dy plus sine y dz. So automatically we have to put it in three different position vectors. For dx we'll be putting sine z, for dy we'll be putting minus of cos x, and for sine y we'll be putting sine, for dz we'll be putting sine y. So now we are going to proceed with the process. Simple process. We have to do the determinants, and with the help of the determinants you are going to find out the curl. So the curl comes out to be cos y I cap plus cos z j cap plus sin x k cap. I'm not going into the details of the curl because we have already discussed how to figure out the curl and everything. So if you haven't gone through it, I will tell you to go watch the previous videos of vector calculus, which I have already demonstrated, and there I have already spoken about curl. So next we are going to find out the n cap and the ds. Remember, when we were discussing surface integral, we already talked about finding out the ds, and we said that it depends on the plane in which we are targeting. If it is an xy plane, it should be dx dy divided by modulus of n cap and k cap. If it is yz plane, it should be dx dz divided by modulus of n cap and j cap, and like that we were discussing about this particular things. So anyways, now we are coming into this particular question. We will be using the exact same point in order to figure out the ds and n cap. Now as you can see, according to the figure and according to the question given here, the z is ranging to 3, and as you can see, if you draw a particular 3D figure over here, as you can see, so it is from z equals 0, because this is basically an xy plane. So here you are getting z equals to 0, and this point should be where the surface is having z equals 3, because we have now gone 3 units upward in the z-axis. So this is the particular parallel pivot, and this is the particular thing that has been given to us. Now we have to figure out a way in order to find out the integration. Now, as you can see, we have drawn another part. This is basically the xy plane surface of this particular parallel pivot, and here, as you can see here, this is OABC dash. So this is basically OABC dash. So this particular plane has been drawn over here. So O is basically the origin, so it's 0, 0. A is pi 0, 0. So A will be here pi 0, because we are only considering x and y plane. And B will be here again pi, and it will be 1, because we have ascended 1 unit. As you can see, 0 to C is 1 unit, so automatically A to B will also be 1 unit. So B will be pi 1 and C will be 0, 1. C dash will be 0, 1. So this is basically that particular section that has been drawn over here. So anyways, that has come to this particular portion. N cap will be equals to K cap, because we are considering the outward normal, which is parallel to that of the K cap. And then we are considering ds will be equals dx dy by modulus of n cap k cap, because here as you can see, ds is the particular plane for the xy. So if you are considering the xy plane here, you have to consider dx dy, and this is the formula for this. So n here stands for k cap, so it will be basically k cap dot k cap, which is nothing but 1. So ultimately we are left over with dx and dy. So this is for finding out the curl, the ds and the normal n. So 3 things we have found out in step number 1. Now let us go to the next step to find out the path of integration and put the limit. Again, very important part. Without this part, you won't be able to proceed further. You have to put the integration limits in order to proceed with the integration. So now for this, we have considered both the cases for x and y. And this will be considered with this particular diagram, as you can see here, this particular diagram. So we have taken this particular surface of x and y, and as you can see, the limit of x can be easily judged from 0 to pi, 0 being the origin and pi being the outer limit of x. And for that of y, now the strip here, it is from P to Q, and this strip is basically from here to here. So here you can see here y is 0, because this is just the x-axis where y has nothing to do. So y will be 0 in the x-axis, and here you can see y will be 1, because this is y equals 1 in this particular line. So from 0 to 1, that will be the limit of y, and from 0 to pi, that should be the limit of x. So this is what has been given over here. We have considered the strip for this purpose so that we can get the limit of y, and for x we can directly conclude it is from 0 to pi. Now we know the particular limits. Now we can easily put the limit and we can get our desired answer. For this, we are applying Stokes theorem. So as we have discussed, Stokes theorem is basically the transition where the singular integration is converted into the double integration. So this particular closed integral f dot dr, which has been given in the question, as you can see, this question, this is the particular thing which we are searching for the answer of this one. So we have to consider this one, and then we will be converting this into this nebula cross f, which also we have already found out, which is cos y I cap plus cos z j cap plus sin x k cap. Now we are going to put the value. With that, we are going to put n cap. We also found out what is n cap. This is nothing but k cap. And then ds also we have got. What is ds? ds is dx dy. So we are putting everything on the next step. So as you can see here, now we are considering r instead of s, because now we are considering that region where we are conducting the experiment. As you can see, this region is nothing but r. So we are considering this particular region where we are conducting the experiment, and with the help of this particular region we will be going through and getting the answer. So now we have put the value cos y I cap, cos z j cap, sin x k cap, and k cap for n cap, dx dy for ds. Now we are proceeding with the next. So now we are putting the limits. So limits are y equals 0 to 1, x equals 0 to pi. And now what happens here, see, as you can see here, I cap, j cap and k cap, and there is only the k cap. So k cap is only going to function if there is another k cap and whatever component lies with that. So I cap, j cap will be cancelled immediately, because there is no other component of I cap or j cap which is functioning. So for the dot product, we are only getting sin x and dx dy will be remaining. So as you can see here, sin x dx dy. Now we are going to put the limit. So first of all, we are going to do sin x dx, and with this we are going to put the limit. Again we are going to do the dy portion also, and finally the answer that we are getting here is 2. So with this we have completed this particular question. Again, I'm repeating the steps. First of all, we converted the line integration or the singular integration into the double integration. For that, we first of all found the curl, then we found out the outward normal, then we found out the value of ds, and then we simply converted with the help of Stokes theorem. And yes, we did find out the path of integration also. So anyways, this will be the end of today's video, and with this we are wrapping up vector calculus. The next video will be starting off with another topic. So I will be discussing very soon what topic we'll be going for in the next module. So until then, this is Rahul signing off. Take care. Bye bye.